Okay, so my name is thank you very much, Peter. My name is Alex Schulman. I'm the co-founder and the CEO of Saccade Vision, and very happy to present Saccade during the inVISION Metrology Day. Saccade Vision is a startup company. We started just 3 years ago, but we already started deploying our solutions with different customers. We develop quality control solution for precise manufacturing with a focus on fast, accurate, and robust measurements. Main applications that we focus on are automated assembly and precise parts manufacturing after precise machining, metal forming, plastic injection, and 3D printing. So I will talk a little bit about challenges that are there when inspecting precise machining. And today, the main option to control dimensions is still using offline inspection with CMM. Fast optical 3D inspection of precise machining typically has several challenges. It requires highly precise and robust measurements, typically below 10 micron accuracy, some would say even well below that. The surface is usually very, very shiny and often limited. The optical inspection is often limited by environmental conditions such as vibrations, temperature, but also dirt, oil, and coolant residuals. Tool marks, even on a very precise surface, represent a significant challenge for optical systems. And on top of that, if we want to integrate metrology inside the manufacturing machine, it would typically require a very small footprint. So this often limits scanning with additional precise motion system. Let's look on those challenges one by one. The main problem with highly reflective materials is strong specular reflection, which is combined with very low diffused light. So this causes a strong camera saturation in certain regions and the lack of signal in other regions within the same field of view. Tool marks create additional directional reflections, saturating certain part of the image. So those artifacts may distort the point cloud and result in certain regions not to be imaged robustly. The effect of oil, coolant residuals this may affect the accuracy of optical measurements, depending on optical characteristics of the residual layer, of course. So, Saccade developed a static profiling scanner that uses a special MEMS mirror to project a laser beam. In some senses, it is like an automotive LiDAR, but unlike typical LiDAR, the laser beam is controlled in all directions. Such laser beam control enables absolute scanning flexibility and scanning optimization per region of the inspected part. As you can see, we align the system and then optimize scanning direction. I hope you can see the video there. Illumination and scan density depending on the inspected feature. In addition to that, we have implemented a proprietary solution that eliminates laser speckles and strongly reduces variation of intensity. We use the ability to focus on regions of interest with a very high sub-pixel 3D resolution without generating huge point clouds, and actually being able to create point clouds with variable density is one of our benefits. Effectively, we can reach local resolution of 10,000 by 10,000 pixels, but it would be not feasible probably to do it for the full field of view. However, if we want to reach high local resolution on a small region, this would definitely be feasible. Flexible laser control also allows achieving dynamic range that it will be few orders of magnitude higher than traditional laser triangulators. This high dynamic range helps us to work on both specular and diffusive surfaces and inspect challenging materials in the same field of view. Flexible laser beam control also allows scanning optimization per region. Together with multiple cameras, it improves visibility and helps to optimize the image acquisition on edges. For example, as you can see here, it is much better to scan horizontal edges with horizontal scanning direction and vertical edges with vertical scanning direction. And finally, scanning with Saccade static profiler minimizes the overall system footprint and increases the scanning speed, since we do not need to move part or move the whole sensor. We just move the light, and we can focus the light on a specific region. Let's see an example of using Saccade scanner for dimensional inspection of precise machined part. As you can see here, this is an extremely shiny part with difficult milling marks. To avoid image distortion and missing or wrong information in the point cloud, we do the following. We optimize scanning direction per region in the field of view and use different combinations of cameras to reduce saturation and eliminate noise. Both laser power and integration time can be adjusted locally for region, offering high dynamic range. And separate partial scans are combined with a single-digit micron precision without into one point cloud. That's what helps us to reach point cloud without dropouts and without saturation. The result is high quality and accurate point cloud, as you can see here. Measurements are environment to the azimuth. We see below 10 micron accuracy when inspecting sphere radius while rotating the target. You can see here. Dimensional accuracy on 150 millimeter field of view is better than 5 micron with 0.01% linearity. That was tested with our software and with our hardware. As mentioned above, the presence of oil and coolant residual shall not affect the quality of inspection. And this test that we performed here is an important part of tool validation. The method we used here was scanning the same part with and without residuals, oil residuals, matching point clouds, and then looking at the local mismatch of point clouds in the area of residuals and compare that to other regions of the part. So for typical residuals that are thinner than 50 to 100 microns, we found that in both cases, point clouds uniformly matched with deviation less than 10 microns. Another important use case is fast optical inspection of cutting tools. In this example, Saccade Vision used wide angle sensor with 300 millimeter field of view. We scanned this blade with low resolution to inspect planarity, and then the same unit focused on a single tooth profile with high resolution. In this case, we are inspecting carbide tip dimensions reaching below 20 micron in all three dimensions. So to summarize, while developing the Saccade technology, we had in mind precise and robust solution for difficult sharp parts. We hope we are able to achieve that. We started shipping our systems, first systems, end of last year, and we are now having quite a lot of customers, new customers, and a lot of interest. We are going to showcase this during the upcoming control exhibition, and we'll be happy to meet you there. You can use the QR code to schedule a meeting with us during the exhibition. So bring your parts and we will be happy to make a live demo for you. And thank you very much for your time.